I'll be presenting my experience in rewriting services in Rust at TikTok. I think compared to many of the previous speakers, my talk will be more broad. It'll be covering quite a number of topics, but less in depth compared to the previous speakers. And so a quick word about me. I'm a CS undergrad at NUS, so not very fancy, just like most of y'all. Not a creator of some JavaScript framework or the engineer at Jane Street, just a guy. So some interests that I have. So I enjoy doing runs outside my serious computer science major. So that's a picture of me finishing my full marathon last year, and I hope to improve my timing this year. And I'm also a big fan of sci-fi films such as Interstellar, and I love eating noodles. Okay. So how did all this get started, right? So a few months back, I was interning at TikTok, and I was getting really sick and bored of writing Python and Golang. So I got really deviant and started looking at the state of Rust in TikTok, and I was really bold to write it in my weekly report. And the following Monday, my big boss, he was standing behind me and staring at me. And there I thought I really screwed up and I was going to get fired. But okay, fortunately for me, I was not getting fired. So he basically asked me, yo man, I saw your report about you're exploring Rust at TikTok. And we have something at hand that perhaps you can look into. So basically we have this service at TikTok that was basically frequently raining CPU threshold alarms where the service was hitting like 90+ percent CPU threshold. And that was because it is under very high volume. So some of the top QPS methods, they reach up to millions of QPS. And he was asking whether I can do experimental incremental rewrite. So rewrite parts of it, the methods that was under the heaviest load in Rust, and see whether it's a viable approach to the problem that we had at hand. Okay, so why did we pick Rust? So I think Rust is the most performant programming language that you can get while still having memory safety. So when I talk about Rust, I'm strictly talking about safe Rust. So the biggest reason is, of course, performance. So how does Rust achieve this level of performance? Well, there's several reasons, and the top reason that I can think of I listed over here. So Rust compiler performs aggressive compile time optimization thanks to the help of LLVM, and it offers a lot of zero-cost abstractions that you can write. So what it means is that by utilizing this language functionalities, you basically get a performance that is better, that's at least as good as compared to writing it by hand. So some example of that would be function inlining, where you use like map, filter, all those things, and then devirtualization. So if you write a function that takes in a trait object, the compiler is able to generate multiple versions of that functions at compile time for each time you call it with a different implementation of that trait object, such that the function address of the method is resolved as compile time rather than having the need to look up at runtime through a virtual table. So another reason is that you have more fine-grained code control because Rust is a low-level system programming language. So a common examples that are given is that you can decide between stack versus heap allocation. For example, like box or RC, and you can give compiler hints to the compiler to generate more optimized code. For example, you can annotate a function inline such that the compiler will inline the function instead of calling it at runtime. And those of you who have taken CS 2.0, you are aware of CPU branch predictions. So in Rust, you can annotate specific branches as code so that it generates assembly that optimizes for CPU branch prediction. And the last reason that's often brought up is the fact that you do not have this runtime overhead from running garbage collection. I don't really agree with that point because I feel that whenever you do something, you have something to gain and you have something to lose. And in the case of Rust versus Go, a lot of optimization has been done for the Go garbage collector. In fact, I think recently Go version 1.35, they had this experimental garbage collector that's like 40% faster than its existing implementation. So when you accept the overhead from garbage collection, it allows you to write certain code that could be more performant, for example. And I'll be talking about that later. Okay, so I'll be sharing a few high-level approaches to the rewrite. So for the context, we're talking about like incremental partial rewrite. So only part of the service is being rewritten. So before I jump into that, for those of you who are not familiar with microservices, this is like a typical microservices architecture. The part that is relevant to us is the bottom chunk, the service mesh. That's how your services communicate with each other in your microservices. So they communicate each other with sidecar proxy. And then the most important feature relevant to this talk is that you can configure traffic with when you're using service mesh, which will come in really handy later. Okay, so the first strongman approach is, why just write a new service. So you have, let's say, functionality method ABC, and instead of, you can just put that in a new service and then call it a day, right? It is the easiest to implement, but it's the most problematic to migrate because all of your upstream services. So upstream is the services that is calling you, that they depend on you. So they need to modify their code to call your service instead of the original service. So this is problematic because it introduces points of failure. So for example, if your implementation is faulty, something's wrong with it, then all the services that depend on you, they have to roll back such that they call the legacy service instead. So you are you're basically offloading the problem to someone else. So it's not a very good approach. The second approach is the approach that I went with, and that is basically you develop in the same existing clusters, existing service, but then you deploy your Rust implementation in a new cluster. So this approach is I think overall the best because first of all, there's no need for upstream changes. So previously we mentioned that you can configure the traffic in the service mesh. So I can update the service mesh such that for the methods that I have rewritten, for example, ABC, then those traffic will be rerouted to the Rust cluster instead of the default cluster. So from the perspective of the upstream, nothing has changed. Your service remains as a black box, and you only need to care about your own service. So for example, if something wrong, my Rust implementation is faulty, I just need to change back the traffic management configuration and all is good. Another added benefit is the fact that you can reuse any existing end-to-end test. So if all those tests are passed, then you can be confident that your new implementation is correct. And then the third approach is something it's a lot more niche and doesn't really apply to my case. But if you have some common logic that is used across multiple services, you can rewrite this library as a Rust crate. So, and then you can call it from the Go side using this C interrupt that Go provides called cgo. So you can generate the corresponding C bindings using this cbindgen library. Then you can just directly communicate with each other. So, but there's those of you who have worked with cgo or you're familiar with cgo, you must be screaming right now. There's a non-trivial overhead to using cgo. So if you are calling this function inside a loop, for example, then the added overhead of calling or using cgo will be added to the point that you basically lose all the performance gains you earned from rewriting this library in a more performant language. So option 1 really applies if you are rewriting a method call that is you perform one time and then it does something CPU intensive once and that's it. But for other cases where you need to call something in a hot path, then you might need to resort to the option 2 where you need to have some sort of low-level integration. So in order to avoid the overhead of cgo, you need to use this low-level integration, and an example would be the Sonic library that is developed by ByteDance. So ByteDance wrote this very fast JSON serialization library, and it's partially written in Go and partially written in C. The way it is able to achieve low-level interop without any overhead is really amazing. So Sonic is a JIT, just-in-time compiled engine. So it writes all the marshalless and the unmarshalless for the primitive types, and then it in C, and then it pre-compiles it to AMD 64 and ARM64. And then at runtime, it will scan through the JSON struct that you have, and then glue together all the function calls to the C libraries, and that's how they achieve this blazingly fast speed. Although, because of the new Go version 1.25 that they released, they had this JSON V2, so it's not really that much of a performance gain. But if you're using the V1, it's like a 5 to 15 times performance gain. So let's pretend Go version 1.25 doesn't exist. Okay, so now that we have the high-level strategy in mind, it's time to proceed with the rewrite. So the most important part about the rewrite is that it needs to be aligned with the Go implementation. It needs to be logically consistent, and the behavior is identical. And there's some blockers to this problem. Those of you some of you might already hear about the fact that the TypeScript compiler is being rewritten from TypeScript to Go. And the tech lead of TypeScript, they were being interviewed about this change, and of course he was asked about why Go, Rust is the new hot thing, why not write it in Rust? And he basically mentioned that the change is a pot instead of rewrite. So it's a line-by-line change instead of a rewrite, which may require some low-level, some code change that will make the rewrite take longer than it should. And this is because of the compile time checks and various kind of restrictions that the Rust compiler imposes on you. So for example, you can't easily implement a cyclic data structure in safe Rust, and also so that will limit the kind of the program that you can write, and it will not be identical. And another common problem that you might encounter is the fact that how null value is represented in Go. So Go uses zero values or pointers, nil pointers, whereas you can express exactly what you want in Rust using the option generic type. And of course, you need to be mindful about the libraries and crates that you use. They may have some differences. And of course, the rewrite, the whole point about the rewrite is performance. So it'll be very embarrassing if you rewrite the whole thing and it's not as good as the Go implementation. So when I first started the rewrite, I wasn't a very good Rust developer. So I made a lot of mistakes. For example, doing a lot of memory operations. So as I was benchmarking my implementation, and I was looking at the flame graph, I can see that a big chunk of the time that the program spends is basically copying memory. So you want to reduce memory operations by using pointers, but because of that, you need to deal with the borrow checker. So pros and cons. You gain some, you lose some, and also of course you can adopt this data-oriented design. It's a very fancy term for a simple concept. So you want to optimize your CPU cache usage. So how you can do that is by optimizing your memory usage. Okay, how do you do that? There's several approaches. First approach is to reduce the data structure size. So by having your structs smaller in size, you can have higher cache rates. Yeah. One way of doing that is by not memorizing certain operations. So those of you who have taken CS 2040S, I'm sure you're aware of the concept of memorization, but I'm here to tell you that you shouldn't always memorize, because at the end of the day, our program runs on hardware, not hardware runs on program. Sorry about that. So if you have some trivial computation that you can do, for example, a strongman example would be you store the beginning of an array, the length of the array, and the end of the array altogether. Obviously, the end of the array is you don't really need to store it because it can be trivially computed by adding the offset to the length to the start. So this is an example of not memorizing certain operations in your data structure. So the reason why it is better is because your CPU registers, they are faster than even your fastest cache. So doing repeated trivial computations is actually faster than reading from memory. Okay, step 2. So now that you have implemented your program in Rust, you have to make sure that it's in fact correct. So performance doesn't matter if the program is incorrect. Pretty straightforward. How did I went about doing it? So the approach, there's various approach you can go about doing this, but the approach that I took is basically capturing the incoming traffic request in production, and then replay it in staging environment to the Rust implementation, and then you diff it against the Go implementation. So you see the difference in the response, whether it's the same or not. If it's the same, then it may be incorrect. But there are cases where there might be false positives. So on top of the test group is your Rust implementation, is the group that you want to test. The control group is the correct implementation, which is the Go service. And then you also need another reference group, which is also the same Go implementation. The reason why you need another reference group is because there could be race conditions. For example, if your service depends on external source of data, such as maybe some relational database or Redis, then it is possible that in between the reads that is performed by the test group and the control group, the data is altered. Then the response that is returned from the test group and the control group, they might be different, even though your implementation might be correct. So this is a false negative. And the way you check for that is by having a reference group. So if both the reference group and the control group returns different response, despite the fact that they're both correct, then you will know that it's a false positive. Yeah, it's a simple idea. Okay, now that you're certain that your implementation is correct, it's time to stress test and find out how much better is it. So I did some stress testing in the staging environment, but you can jump straight to the testing in production environment. So you can do some stress tests in the staging environment to gauge roughly what's the performance like. You can do some profiling and identify bottlenecks and then optimize your implementation. Once you feel you're ready, you can jump into stress testing in the production environment. Why stress tests in the production environment? I know it sounds a bit dangerous, but it is absolutely necessary because your production environment might be different from your staging environment. So you can't control that. So it's best to test in the production environment. So there's two goals that you want to achieve in your stress testing in production environment. So first of all, you want to find out what's the peak QPS that both implementation can achieve. But apart from that, you also need to identify what is the maximum sustained QPS that both services can achieve. Because let's say you just increase the QPS until your implementation fails, that's the maximum number it could achieve, but it doesn't necessarily mean that your service can maintain that peak level of QPS, for example. So in real world, your service will be under load constantly for like a prolonged duration. So you need to ensure that you need to find a number such that your service is able to handle comfortably. Yeah. And very useful tip, mock your downstream to avoid DDoSing your own service. Please do that. Also, it's good to test on more instances because at the end of the day, your physical machines, the host machine may have slight differences. The compute providers, they might over provision the CPU, so you might not even getting the number of CPUs that they promised you. So the way you avoid that is by increasing your sample size and you get more accurate data. And yes, of course, I forgot to add, when you are stress testing, please inform the person who's on call so that he doesn't, when I did my stress test, the staff on call, he looked like he wanted to kill me. Yes. Okay, final step, migration and monitoring. So now that you have stress tested your implementation, it's time to start the migration. Yes. Okay, so it's good to have this kind of gradual traffic migration strategy. So you start with 1% of the traffic that goes to the Rust service. So your current implementation, Go implementation will handle 99% of the traffic, while Rust handles 1% of the traffic. Then 2, 5, 10, so on and so forth. So that if something goes wrong, damage is limited to like a very small portion of the traffic. It's just a safety measure. And then in order to detect any discrepancies at runtime, you need to add additional logic. So you take 1% of the 1% of the traffic. So 1% of the incoming traffic to the Rust service, and then you diff it. You make a request to the Go service, then you diff it again. So you check whether it is in fact correct, because it is, although unlikely, it is possible that during your correctness check at step 2A, you might have missed something. And there's also, in my case, I needed to run this like forever. It is because it is impossible for me to deprecate the Go implementation, because there are certain upstream services that bypass the service mesh entirely. So basically, the approach 2 that I talked about, not very valid, but it's valid for 99% of the time, and that's good enough. Yeah. Okay, so I feel I'm going too fast. When I did it in my own free time, I should be around 30 minutes mark. Okay. So what are the results? So lower latency. I think on average the latency is lower by 30%, but the P99 case is like 76% lower. But it's really not noticeable from the perspective of the client, because your network latency dominates like your server-side latency. So the more impressive result is the fact that I was able to double the throughput. So for the same number of virtual CPU core, my Rust implementation is able to handle twice the throughput. So if you do some quick math, that just means that with the same number of, you can handle the same throughput by using 50% of the compute resources. And the real world implications of that is if the traffic in regions outside of US and EU, so there's like in US compliance region and outside EU, so the rest of the world, if ever is fully migrated and you run it for an entire year, it will save $300,000 in terms of cloud compute costs. So and this is only possible because of the scale that TikTok operates at. So if you have, for your own side projects that has one test user, that's yourself, it's not going to make a difference. Okay. So what is the takeaway? So first of all, given that amount of effort I put in, I would have expected at least 10x the performance, but reality is very often disappointing, and I only get 2x the performance. So Go is not that slow compared to like this low-level system language. At the same time, Rust can be really slow if you write really bad Rust, like how I did when I first started out. Skill issue. It's a real problem, and you have to consider this, because a lot of times when people compare Rust and Go and how you can like write so much more performant code in Rust, you don't really take into account the fact that given the same programmer, the same programmer might be able to write better Go code as compared to Rust, where he might encounter a lot of compiler errors. And as humans, we would like to take the easy way out, and we write code that's less performance. For example, you pass the ownership of a struct everywhere instead of passing a mutable reference, for example. Then your Rust code can be really slow, or for example, you clone everywhere. Yeah, and the second takeaway is, of course, I think it's often talked about, is how when we talk about the performance of a language, we should not just look at the system performance, so how fast your code, your service is able to run, but we also need to look at the engineer performance. So Go is the language that I would call the 80-80 language, where it achieves 80% of what you could get in both regards. Whereas if you do something in Rust, you might get 95% of the performance, and you compromise on your engineer performance, and then Python is the other end. So if we take that into real life, right? For example, if you are an engineer and let's say you can handle 3 business features in one quarter if you do it in Go, but it's less, less performant. Whereas if you do it in Rust and you can only handle 1 business feature, I think most career-oriented engineer they will go with the first approach, the first option, because that's more beneficial to your OKR or your KPI, your performance review. From the perspective of managers, it's much easier to handle to hire Go engineers. If not, you can quickly onboard someone to use Go within a week. Whereas if you want to hire a Rust developer, it's much harder. And if you want to train someone to be proficient with Rust, it might take a month or even 3 months. So a lot of real-world implications that we need to consider when we talk about Rust versus Go. Yeah, so I feel like I've been saying Rust is not good, but there are times where you should consider writing or rewriting something in Rust. But again, try to identify the bottleneck first. So the problem could be addressed without the need to rewrite it in Rust. So you can optimize your existing implementation, or you can add middle layers or CDNs or whatever, all those techniques to improve the performance of throughput of your service. So a very good case study that you guys can look into is another Friday Hacks talk, where the engineer of Node-Flare, I believe, he's able to scale out to 400,000 users using Ruby on Rails. If you can do it on Ruby on Rails, you can do it in Golang, man. You don't need to do it in Rust. But okay, so what is the criteria to where you should write something in Rust? This I would call the criteria I would use is like economies of scale. So if the usage of your tool, of your service, of your library is very high to justify the man hours. For example, all the JavaScript toolings that you see nowadays is being downloaded from NPM millions of times a day, then I would consider a worth price to pay to justify the man hours. Another criteria is that the code is rarely modified. So you only go through the pain of writing it in Rust once, and that's it. You just leave the code there, and it will run blazingly fast for the rest of its lifetime. Okay, 1 minute early. Thank you all.
Questions?
Oh yeah, any questions? Yeah, yes please. So let me just repeat your question. So you're asking how complex the code base is, right? In Golang.
So what the process of rewriting it is, how long did it take?
Okay. So the Go service itself is not too complicated. So it's actually, you can consider it as a caching service. So most of this task that it's doing is basically it will do some checks, and then it will read from Redis, and then deserialize it from protobuf, and then do some matrix emission, and then return to the caller. Most of the complexity came from actually a lot of the libraries that it depends on. So because the ecosystem of Go is quite well developed, whereas the ecosystem of Rust is less well developed. So a lot of libraries that the existing implementation depends on is not present in the Rust implementation. So a lot of the crates needs to be rewritten, and yeah, so that's mostly the complexity. It took me, I can't really give you an accurate gauge of how long it took, because I was spending 50% of my time. Okay, if it's 50%, I guess I'll just divide by half then. Then it's 2 weeks. 2 weeks, yeah. 2 weeks. Yeah. Are you satisfied with the answer?
Sorry, one more question.
Okay, sure.
So given that it's doing so much reading from Redis and deserializing, so how do you pinpoint where most of the secrets like this? Is it a matrix conflict?
Oh no, I was doing like, I generated a plane graph from one of the pods. Then I'll look at like what's the CPU time spent on. And then I saw, okay, mem copy, reduce mem copy.
So I'm more of a guy about maths. I just wanted to ask like probably two questions. How did you derive the 300,000 cost savings? Like, and then was that is that more of a specific region based on how will that change? How will it change?
Okay, so you're asking me how did I come up with the $300,000 and then whether the cost will be different in different regions, is it?
I assume it will, but
Okay. It's actually not as, it's very straightforward. So whenever you scale out, you increase the number of virtual CPU cores that you use on the internal website where you can manage your instances, your compute instances. It will tell you how much it costs per virtual CPU core. So I just took that and I multiplied the number of cores I will be saving, and then times 365. Yeah. No, I would. It makes sense now that you asked that it would be different, since the cloud providers in EU and in US, I think some of them is Oracle and some other. So it makes sense that they will be different. But I only calculated the cost in ROW in Singapore and its neighboring regions. Yeah. So that's a great question. Okay, if you have any other questions, you can also message me on LinkedIn. You know, it's